equal to, this is equal to, take the matrix S1, S2, Sn and multiply it with the diagonal matrix lambda 1, lambda 2 up to lambda n, 0 and 0. Okay? 0 here and 0 here. And if this is the case, that means you get the matrix P here and D here. So this shows that AP is equal to what you call PD actually. In other words, that A is similar to a diagonal matrix. D. How about converse? Y, if A is similar to what do you call a diagonal matrix D, then what? So let's think about the converse actually. In the converse, we have to assume this. In other words, we have to assume that there is an invertible matrix P, okay, for which A can be written in this manner. Then if you, from that invertible matrix, okay, and A, you can constitute a basis for Fn actually. We can constitute a basis for Fn. So say that P is this S1, S2, Sn matrix, okay. This P is not same as this actually. So we're not assuming that these are S1, S2, Sn are eigenvectors actually. Okay. Let's talk about now the converse. Okay. Let's prove the converse. So for the converse, what we have to assume, we have to show that there is an invertible matrix P such that, and a diagonal matrix D such that A can be written in this manner actually. Okay. So let's take a matrix P, and it's S1, S2 up to Sn. Keep in view, now S are not eigenvectors actually. So they are just column vectors of the matrix P. And D is some diagonal matrix. Okay? In other words, there are some non-zero entries on the diagonal of the matrix actually. Lambda 1, lambda 2, lambda n. In the converse, I'm not assuming that these are the eigenvalues actually. Okay, these are not eigenvalues for now. We will see that later on there will be eigenvalues and these are going to be eigenvectors and this is going to give us the basis. But for now, P is some matrix, n by n matrix that is invertible, and D is a diagonal matrix actually. And we have this identity that A is equal to P, D, P inverse. Okay? A is equal to this P, D, P inverse. Now, if this is the case, now this is the case, then what? First of all, what would be the rank of this matrix? So, this is an invertible matrix actually. So, if the matrix P is invertible, okay, let me say that as P is invertible, so, its rank is equal to n. That is, these vectors, the columns of it, S1, S2, Sn, they constitute a basis for Fn. Okay, so we already kind of deduced that, there is a basis for Fn. The only thing that now we have to deduce that these vectors S1, S2, Sn are the eigenvectors corresponding to lambda 1, lambda 2, lambda n actually. Okay, and how can I show this? I'm going to use this identity. So let's compute AP. So the AP is really AS1, AS2 up to ASN. Okay, and what? And this is equal to this is equal to dp, where the dp, when you're going to multiply the matrix d and p like you did here, okay, you're going to get what you call lambda 1 s1, lambda 2 s2, lambda n sn actually. You're going to get lambda 1 s1 up to lambda n sn. Now if these two are equal, that means that these entries are equal actually, corresponding entries are equal. In other words, ASI is equal to lambda I SI. That these S1, S2, Sn are eigenvectors. They are eigenvectors of A, and we already know that they constitute a basis for Fn, and this is what that you needed to prove actually. This is what that you needed to prove. So if you keep this basic result in head, okay, so we proved the previous lemmas so that we can reach to basically, this basic result, and this basic result tells you that your invertible, your matrix, and by square matrix, is similar to a diagonal matrix, okay, if its eigenvector forms a basis for Fn. Now, how to find that, diagonal matrix to which a given matrix is similar? No worries. Find its eigenvalues and put them on diagonal. So this is going to be the diagonal matrix to which the matrix A is always going to be similar. And where are those eigenvectors? Okay. In other words, from where to find this matrix P, the similarity matrix P. So corresponding to each eigenvectors, compute eigenvalue, compute eigenvectors, and put those eigenvectors in columns and make a matrix actually. So this is going to be the similarity matrix, which is going to satisfy this identity. In other words, that A is similar to the diagonal matrix D actually. So for finding that A is similar to what diagonal matrix? D. And what is this similar matrix A? You don't have to do anything. Just take A, compute the characteristic polynomial. What are, what are the roots of it? Take those roots, make a diagonal matrix. So this is going to be the diagonal matrix. And corresponding to these roots, okay, you must have, eigenvectors. Take those eigenvectors, put them in a matrix, so you're going to get the matrix P actually. And hence you can easily find a matrix, D, which is similar to the matrix A actually, with the similarity matrix P actually. Okay, so this theorem is going to is giving you a recipe to compute to diagonalize the matrix actually. I'm going to be a bit more precise now. Let's define what do you mean by the diagonalizing a matrix actually. So let's put a definition. So a matrix A from Mn F is diagonalizable. Okay. Diagonalizable if there exists a diagonal matrix D, diagonal matrix D such that A is similar to this diagonal matrix. That is, there exists an invertible matrix P from Mn, okay, invertible matrix, such that A can be written as, PB, P inverse or P inverse dP doesn't matter. Okay, so you're going to say that A is diagonalizable. In other words, A is diagonalizable if you can factorize A in the terms of these, in such a form where P is an invertible matrix and D is some diagonal matrix actually. So if you can write A in such a form, you're going to say that you have diagonalized the matrix. Okay? And in this theorem, we already saw that how to diagonalize a matrix actually. So you need to find what? You need to find the eigenvalues of the matrix, put the matrix A, put those eigenvalues in and make a diagonal matrix out of it, compute the eigenvectors associated with these eigenvalues, and then make a matrix P, and then you're going to see that you can check actually that A is going to be similar to this diagonal matrix D with the similarity matrix P, and hence A is diagonalizable. Okay, so it's not difficult to find matrix P and D actually, so that's important. One of the corollary of this theorem is, okay, one of the corollary, I mean, you might have already observed actually, okay, you might have already observed that in order to diagonalize a matrix of order n, the matrix n must have n distinct eigenvalues. So if it has n distinct eigenvalues, you can diagonalize it. And actually, you can prove a necessary and sufficient condition that you can only diagonalize a matrix, n by n matrix, if it has n distinct eigenvalues actually. So if it doesn't have n distinct eigenvalues, in other words, if you have a 3 by 3 matrix with the 2 eigenvalues, lambda 1 and lambda 2, you can't diagonalize it. So 3 by 3 matrix can be diagonalized only if you have 3 eigenvalues, 3 distinct eigenvalues for it actually. Okay? So the corollary is that if A is Mn, then okay, A has n distinct eigenvalues, then A is diagonalizable actually. Okay? Because it is pretty easy to compute the diagonal matrix and matrix P for it actually. You just have to take the eigenvalues, put them in diagonal matrix, and compute the eigenvectors, okay, associated with each eigenvalue, make a matrix, and hence you can diagonalize it actually. So let's let me give you a necessary and sufficient condition for a matrix to be diagonalized. So one, we already have a sufficient condition that if it has n distinct eigenvalues, it is diagonalizable, but this is necessary and sufficient condition. And the necessary and sufficient condition is that a matrix M, a square matrix n is diagonalizable, okay, diagonalizable if and only if, okay, if and only if for each lambda, which is an eigenvalue of the matrix A, we have algebraic multiplicity equal to the geometric multiplicity. So you can only diagonalize a matrix if for every eigenvalue algebraic multiplicity is equal to the algebraic multiplicity is equal to the geometric multiplicity actually. Okay? So what is the proof? By the way, converse we already have done it. Why? Because we proved the result that if the algebraic multiplicity is equal to the geometric multiplicity so if A is a matrix for which algebraic multiplicity is equal to the geometric multiplicity, then the eigenvectors of A are going to form a basis for Fn. Okay, they are going to form a basis for Fn. And the last theorem told you that if there are eigenvectors which are constituting the basis for Fn, you can diagonalize it. You can diagonalize the matrix. You can write the matrix in such a form actually. Okay? So the converse of this we have already done actually. That if the algebraic multiplicity is equal to geometric multiplicity, the eigenvectors of vectors A of the matrix A are going to form a basis for Fn. And if they form for the basis for Fn, then you can find a diagonal matrix and a matrix P such that A can be written in this manner. And hence you can diagonalize the matrix A actually. So the converse is simply true. The key thing that I would like to prove is this actually. Okay? The key thing is to prove this. So suppose A is diagonalizable. Okay? So from previous result we know there exists a matrix D which is a diagonal matrix with entries eigenvalues and invertible matrix P, okay, such that A can be written as P D P inverse actually. Okay, so A can be written as P D E P inverse. In other words, A is diagonalizable. So that's what it is. So now I would like to talk about that why geometric multiplicity is equal to the algebraic multiplicity. Okay, why the geometric multiplicity? So what is the geometric multiplicity? Say for example, one particular lambda, where this lambda could be lambda 1, lambda 2, lambda n, anything. Then I know that this is equal to the dimension of the eigenspace of the matrix A corresponding to the eigenvalue lambda actually. Okay? And this is same as the dimension of the null space of, you know, lambda I minus A. Okay? A minus lambda I. A minus lambda I. By definition, this is what is really the eigenspace. Now, I can do an interesting thing. I can do a little calculation that with this matrix A, if I take, say, so since A can be written as S ds inverse, no, P d P inverse, P d P inverse minus, with this term, if I, for example, write lambda P I P inverse, so nothing would change actually. Nothing would change, so it would be still same actually. And hence, this is equal to the dimension of the null space of D minus lambda I, okay, D minus lambda I times P and P inverse I. What we can say now is that this is equal to the dimension of the null space of this. So this matrix is similar to the matrix that you have inside actually. So in other words, I can say that this is equal to the dimension of the null space of D minus, what do you call, lambda I actually. This is what that you're going to get. And what would be the dimension of the null space of D minus lambda I? By the way, this is going to be equal to the dimension of null space of, what would be the matrix D minus lambda I? The D minus lambda I matrix is lambda minus lambda 1, okay, or maybe lambda 1 minus lambda up to lambda n minus lambda 0 and 0 here. This is what that you're going to get, okay, by definition. And what is the null of such a matrix actually? Equal to the number of eigenvalues of A equal to that are equal to lambda. That are equal to lambda. And if this is the case, this is precisely is the algebraic multiplicity of lambda actually. Okay, so in other words, what is algebraic multiplicity? The algebraic multiplicity of say eigenvalue lambda is that how many times this expression appears in the characteristic polynomial. Okay, so it's going to appear into the characteristic polynomial if the eigenvalues, the number of eigenvalues that are equal to what you call lambda actually. Okay, so you can say this is precisely is the algebraic multiplicity of lambda. Okay, and if this is the case, then this is what? This is really a lambda. So g lambda is equal to a lambda. Okay, so this result shows that that you have a matrix So this result shows that a matrix is diagonalizable if and only if for each eigenvalue the algebraic multiplicity is equal to the geometric multiplicity. Now let me give you an algorithm to find that whether a given matrix is diagonalizable or not. Okay, and if it is diagonalizable, how to find its, how to find this diagonal matrix actually, how to find the matrix P and D so that we can factorize the matrix AFD. Okay, so the algorithm to diagonalize the matrix is this. Then let's apply that algorithm on a particular example. So algorithm to find basis, algorithm to diagonalize a matrix A. Okay. So the step one is this: find all eigenvalues. All eigenvalues of eigenvalues and eigenvectors of A. Okay, this is the first step. Second step is check whether these eigenvectors. Okay, so say the eigenvalues that you found are lambda 1, lambda 2, lambda n. Okay. So the step 2 is to check that the eigenvectors, okay, eigenvectors v1, v2, say vn, they form bases of Fn or not actually. So they form bases of Fn or not. If no, you can't. So A is not diagonalizable. A is not diagonalizable. If yes, okay. If yes, you can diagonalize the matrix A actually. If yes, then A is diagonalizable. So second, step is really the step to know that whether your given matrix is diagonalizable or not. In step 3, you can find this factorization. How you can find this factorization? That take the eigenvalues, make a diagonal matrix out of it, okay, and take the eigenvectors that you have found, and they form a basis for Fn. Put them in what you call columns of the matrix P. Then these are your requireds. Then you can check actually that A is going to be P, B, P inverse, okay, and hence you have the diagonalization of the matrix. So what are 3 steps? First, find all eigenvalues and eigenvectors and check whether the eigenvectors form a basis for Fn or not. So if they form, A is diagonalizable. If they're not, you can't diagonalize A. And step 3, once you know that, you can obviously proceed to step 3 if your answer is yes, actually, you can diagonalize. And the step 3 is really that you can take the eigenvalues, make a diagonal matrix out of it,